first problem on continuity equation, you have a water that is running into a fountain and it's filling all the pipes at a steady rate of 0.750 cubic meters per second. The first question is how fast will it shoot out of a hole that is just 4.50 centimeters in diameter? And the second question is at what speed will it shoot if the diameter of the hole is now 3 times as large as the initial 4.50 centimeters in diameter. Now, the first thing that you should note from this problem is that the given 0.750 cubic meters per second is actually your volume flow rate, so that is dV over dt. And if we want to illustrate this problem, initially you have a smaller cross-sectional area, you call that A1, and then you allow or you solve the velocity at a later time in which the same volume is crossing through a larger cross-sectional area here, which is, we will denote as A2. Okay, so that is our problem. But before we solve that problem, let us try to make sure that everything is an SI. In that case, our diameter, which is just 4.50 centimeters, let's convert that one to SI. So that will be 0. Centimeters. So we know that 1 meter is 100 centimeters. That means since I am going to convert centimeters to meters, I have to move this decimal place twice, or 2 decimal places. So I will have 0.0450 meters. So I think the conversion is pretty straightforward and you can do it yourself. Okay, so you have that. Remember also from the continuity equation, so I'll put it CE. Continuity equation actually gives us A1 multiplied by the velocity at that cross-sectional area, and it is just equal to A2 multiplied by the velocity at that specific cross-sectional area. And since our assumption for the fluid is this is an incompressible fluid, so that means the rate at which the volume passes through this cross-sectional area, meaning you have 0.750 cubic meters of volume that is passing in one second in this area, that is also the same flow rate, or that is also the same volume that is crossing through this larger cross-sectional area in 1 second. So meaning, pareha gina silang duha, they have the same volume flow rate. Even if you consider another point here, it will have the same volume flow rate here, or this portion here, they will really have the same volume flow rate because that is based on, or that is a consequence of our assumption that our fluid that we are working with is incompressible. And we also know that these terms here are just referring to your volume flow rate, or that is just equal to the volume flow rate. Therefore, since our first question asks us to find for how fast, meaning the velocity, so we will be working with this expression. A multiplied by the velocity is just equal to the volume flow rate. Since we are asked to find for how fast, then that is referring to the velocity, how fast it is crossing. So we will manipulate that equation and we will arrive at this form, divided by the cross-sectional area A. Now take note that if you try to look into this illustration, the cross-sectional area is actually equal to the cross-section or the area of a circle, since this is circular, which is most of the case. We will deal with circles. So the area is just pi r squared, where r is your radius. So since we are not given with radius but instead with diameter, you recall that your diameter is just twice of the radius. Therefore, your radius is actually half of the diameter. Okay, so when you do that, you are going to replace r with this expression d over 2 and square that one. And hence, you will get pi over 4 d squared. So this is now the cross-sectional area. So this is the area with which you will replace this expression below. So you have dv over dt divided by the cross-sectional area, which is pi over 4 d squared. Okay, so you have that expression now. What you're going to do next is to simply substitute the values. The volume flow rate is given to be 0.750 cubic meters per second. You divide that by this term, pi over 4, multiplied by d squared, and you know that d is 0.0450 meters. Now the next thing you are going to do is to check whether it will give you a sensible unit. So from this, you will see, oh, okay, sorry, this is squared. You will see that you have m squared in the denominator and m cubed in the numerator, so that will leave 1m. So you will have meters per second as the remaining unit, which is sensible. So you are sure that you're actually working with the correct set of equations here, since you yield a sensible result. And plugging in that values to your calculator, you should get, okay, pi over 4 multiplied by 0.0450 squared. Okay, you should get 471.57. You have 471.57 meters per second. So this is the velocity, or this is how fast your water is actually moving through the small a1, meaning the cross-sectional area with the diameter of 4.50 centimeters. Now, if you try to solve for problem B, we actually have a prediction that it will be slower since it already has a very large cross-sectional area. And let's try to solve whether we will really get, or we will arrive with what we predicted earlier. So for part B, we are still going to use these equations above. So the same thing, the same process that you undergo. The only thing here is that we will now have an alternative form for area. So since we are going to use through or go through the same process, I will copy the last step with which we are the same. So kana dv over dt divided by the cross-sectional area A. Now, remember that the cross-sectional area A in this case is given by this form below. So take note that in this case, our diameter 2 now, meaning our diameter in the problem B, is actually 3 times the diameter of the initial diameter, meaning 3 times of 4.50 cm. So our cross-sectional area then will be given by pi, and then our radius is 3d over 2. So this is just the same with diameter over 2, but the only thing is the diameter now is just 3 times the diameter. So you have 3d over 2. You square that. So when you square that, you have pi, and then you multiply that with 9d squared over 4. So you simply take out the constant. So you have 9 pi over 4. So this is just a constant d squared. This new expression for area now is what you are going to use for the problem B, since the diameter is 3 times the original diameter. So you plug in that value here. Oh, let me change the color to yellow, back to yellow. Okay. You have the same volume flow rate because, as I've said earlier, and you know from the discussion, that because of the assumption that the fluid is incompressible, the volume flow rate is constant through all the paths. You have A, as I've said, you just replace A with 9 pi over 4, and then you multiply it by d squared. Okay. Oh, plug in the value. The volume flow rate is a constant at 750 cubic meters, 0.750 cubic meters per second divided by 9 pi over 4. So you don't have a problem with this one since this is already a constant. And then d squared. So d squared is just 0.0450. You have 0.0450, that is in meters, and don't forget to square everything. So when you do that, the same thing happened with the unit m cubed over m squared. You have m over s, which is what you expect for velocity. Okay, now you try to plug in that value to your calculator. You will get okay, you will get 52.396 meters per second, or that could be since we are having the convention that once it's more than 1, I mean the value is greater than 1, we will express that into two decimal places, so we could round that off to 52.40 meters per second. Now let's try to check whether our prediction earlier is correct. So as you can see, the initial velocity at the first cross-sectional area 1 with smaller diameter has a very large velocity there, while the velocity at a larger cross-sectional area has a smaller velocity, which is just 52.40. So that is sensible, and that is what we expect because of the geometry of the problem.